So when, like with the Saturn V and the space shuttles and all these other rockets, they would have these parts that they would get the ship up into space, but they would descend down to Earth and crash into the ocean,
Yes.
and they would never use them again.
That's right.
How do you avoid that? Like, what is the difference between the way these things are structured? Like, the whole thing goes together, and then it lands together?
Well, we're on the wrong planet for a single stage to orbit.
Right.
I think one thing to appreciate is like space. Getting to space is easy. Getting to orbit is hard. So you only need maybe 1 or 2% of the energy to get to space, to where the atmosphere is thin, compared to what you need to get to orbit. And if you get to orbit, now you've got to burn off all that energy, and you're coming in like a meteor. So you need a powerful heat shield. So it's like super difficult to get to orbit at all. And then if you get to orbit at all, then making the stages reusable means they got to come back intact. And then the upper stage is especially difficult because it's got so much energy. All the energy you put into it, you have to take out. So it's you're literally coming in like a flaming meteor, and most things would just melt or vaporize. So, like if you as a human try to come in from orbit, you'd just be pink mist.
Yeah. That's a funny way to put it.
Yeah.
Now, the space shuttle, they had tiles, right? That was the way they avoided the heat. They had these heat shield tiles. What do you use with the SpaceX rockets?
Yeah, we're have a more advanced version of the shuttle tile, but you got to use some kind of ceramic. Essentially, it's usually some form of silicon oxide, aluminum oxide, some carbon perhaps thrown in there.
And is it like a one piece, or is it in tiles? The way
it's in tiles, yeah, we've hexagonal tiles. You can see with each Starship, we've actually increased the size of the heat shield. So it's tough because the tiles are they're kind of like, I don't know, that's not quite the right analogy. They're kind of like dinner plates. Like they're brittle, and their coefficient of thermal expansion is different from metal. So metal will expand and contract differently from the tiles, and the tiles also get super hot, while the metal, it can be super cold because it's got cryogenic fluid behind it. So you got this differential expansion and contraction, which makes the gaps in the tiles expand and contract. But if the gaps get too big, then you get kind of the hot gas, sort of the plasma gets down, but get plasma in the crack, and it's not as bad. And then you're going to melt the metal behind it. So, but if they're too close, then they bang together and they crack. So you've got to get it just right, where the gap's just right, and then they can, the way that they're attached to the body, they can move around a little bit.
So there has to be some sort of room to move. It can't be one large piece of ceramic that you fit over the front.
Yeah, you can't really make such a giant piece of ceramic because you got to. Well, I guess you'd have like a super gigantic oven, but you really need expansion contraction joints. So it'd be quite difficult to do a single piece tile. Think of it like tiles for a roof or something like that. Why don't we just make one tile for a roof? It's like
right,
didn't work.
Now, these things have multiple stages. How many stages in the rocket boosters when things are taking off?
Starship has 2 stages. So it's that's the minimum number that you could do on a planet like Earth. The gravity and Earth's gravity is quite strong, and we have a thick atmosphere and strong gravity. So whereas like if you took off from Mars, it's like relatively easy. Mars is around just under 40% of Earth's gravity. The moon is about 1/6. And getting to lunar orbit from the surface of the moon is easy. During Apollo, the lunar lander, just the top half of the lunar lander was able to take off and get to lunar orbit. But to get to Earth orbit, you need the giant rocket. It's very nonlinear.
So what happens to the first when you take off and it separates into stages? How does the first stage get reused?
Well, have you seen how the Falcon 9 stages work, where they come back and land?
No,
You haven't seen that?
no.
Wow. Um, yeah, I mean,
Jamie's gonna pull it up. So does it come down with parachutes? Does it how does it land?
no, it lands propulsively with the thrusters,
So
with the engines.
Really?
Yeah.
So it's
Yeah.
designed to take off. Here it is.
Yeah.
Oh wow. So that is the bottom of the rocket that launches it straight up, and then afterwards it comes down and lands like that.
Yeah.
That's amazing. And then the top piece can then land separately.
Yes. Well, in the case of Falcon 9, the upper stage burns up on reentry. Falcon 9 has there's the fairing, the top, where the satellites are contained in the top, and that the fairing halves, once it gets to space where the atmosphere is thin, it's still a long way from orbit, but it's in space, so you no longer need the satellite doesn't need to be protected by the nose cone, the fairing, and so that it sort of splits in two and falls away. And then, so with Falcon 9, we recover the fairing halves and recover the booster, but we lose the upper stage.
On purpose? Did you design
well,
it that way?
Yes, but it's not really possible to, if with Falcon 9, the architecture does, like, if we made the upper stage reusable, our payload to orbit would be dramatically less. So in order to have meaningful payload to orbit, scale is important. Like, you need to make things big. There is value to scale. For the family, like for a truck, you wouldn't want like everything delivered by a small pickup truck. You want semi-trailers. You don't see you don't see ships in the ocean, cargo ships, coming along with one sea van and with an outboard motor.
Right.
It's like a giant ship. So scale has value in and of itself. Like the same computer that controls the big rocket controls